Hello, and welcome to our webinar, Casting Technologies. My name is Maurice Hartlieb, and if you have any questions, you can find the email address of Martin Hartlieb and Jay Armstrong at the end of this presentation. In this webinar, we will give an overview of the different, most common foundry casting technologies, we explain their advantages, and give a few examples of typical applications. Within the casting technologies, we distinguish between permanent mold and lost mold casting. So with permanent mold, as the name indicates, we use the same mold to make several or many castings. And lost mold means that we use one mold for one casting, and once it's made, then the mold is gone. Within those technologies, we distinguish between a lot of different variants. So in permanent mold, we distinguish them by the way we fill the mold. So this can be with gravity, that's gravity permanent mold, or with tilt pour. We will explain how that works later. There is also centrifugal casting, low pressure permanent mold casting, high pressure die casting, squeeze casting, semi-solid casting, and there we distinguish between Thixo and Riserless casting. If we talk about lost mold casting, we have to distinguish between permanent pattern, so the pattern which represents the casting is used again to make more sand molds, for example, and then lost pattern, which means that the pattern itself is also lost, and then the mold as well. So with permanent pattern technologies, we distinguish between sand casting, so the mold is made of sand, plaster casting, shell molding, and ceramic molding. And within the lost pattern casting technologies, we typically find investment, also known as lost wax casting, lost foam casting, and vacuum casting. So we can distinguish casting technologies by the way the metal is poured into the mold or die. And that can be, as I said, with gravity, and there's direct pouring into mold with gravity tilt pour, with low pressure, and with low pressure I mean 1 or 2 bar atmospheric pressure to push it in slowly, centrifugal force, that's centrifugal casting, and then high pressure. And high pressure really means very high pressure, where you inject it in a very turbulent way, very, very quickly. The mold is filled in milliseconds and then compressed in the intensification phase with up to 1000 bar. And there we distinguish between liquid high pressure die casting, so that's the typical high pressure die casting we know, or if we inject slowly and squeeze the metal more, that's called squeeze casting. And then semi-solid casting, and here again we distinguish between Thixo and Riserless casting. So if we look at gravity permanent mold casting or gravity sand casting, either way, we pour the metal in as we can see in this animation. And typically we don't want to pour directly into the casting itself, but we have a gating system that allows us to smoothly fill the mold cavity. And if we now look at tilt pour casting, well, there it is actually even more visible that we want to smoothly fill the casting itself. So we pour it in and we slowly tilt the mold, and with this we then get a very homogeneous filling of the cavity in a very smooth way. So now we come to low pressure casting, and here we are filling from the bottom, so we don't just splash the metal into the cavity itself. So below the casting machine, we have a pressurized holding furnace, and as I said, this is a very low pressure of about 1 bar or maybe 2 bar maximum. We can also vary the pressure and thereby vary the speed at which the metal is coming up and filling the casting. As we can easily imagine here, we can actually tailor a lot more the way we fill the casting and at which speed we are filling the mold. Now here we can see a simulation of the high pressure die casting process. This is not real time, and we have actually 3 phases of the high pressure die casting process. The first one, that is shown as light blue, light greenish, is where the metal is in the shot sleeve and the ingates, and that's what we call the slow shot part of the filling process. That usually takes 1 or 2 seconds, but after that, where the other colors start, and each color represents one metal string or stream, and that cavity filling itself is usually just a question of milliseconds. So in this case, it's probably 50 to 60 milliseconds. And then the metal goes into overflows, and in this case, a chill block where we naturally vent or pull a vacuum. And so after that comes the third phase. So we had the slow shot, the fast shot, and now the intensification phase, which is where we put the really high pressure, because this is where we compensate for the metal solidifying and therefore shrinking in the cavity. When it comes to mechanical properties, they are determined by the alloy composition and of course the impurities. We'll see this graph several times in this webinar series, and you can see here that depending on the iron, you can get on a very different curve. So you have a trade-off between strength, in this case UTS, the ultimate tensile strength, and elongation. And depending on how we age it, or depending on the magnesium content in the aluminum silicon alloys, for example, I am on a curve, and I trade in one for the other. So for example, if I age a bit longer, then I trade in elongation, and I gain strength up to a certain point. So alloy composition. That is, of course, the first thing, and impurities. Depending on how many and which kind of impurities we have, we will lose properties, especially with the ductility. You will see this very quickly. Then, the melt quality and cleanliness. I can have the best alloy composition and the lowest impurities in the world. If my metal practices aren't good and my cleanliness isn't good, then the casting will never be good. This is also applied to the ingots that you receive. It's not just about the composition itself, it's also about the quality of the metal that you receive, and then the way you melt it down, and the way you treat the metal, transfer the metal, and then finally cast the metal parts. Then, of course, the casting technology. What type of mold or die are you using? And we will get a lot more into that, because what that really determines is the solidification rate. And the faster we solidify, the smaller the grains will be. The smaller the dendrites will be, and we often talk about dendrite arm spacing. We have dendrite solidification in most cases, and usually you'll see we count the secondary dendrite arm spacing. And the faster we solidify, the smaller these dendrite cell sizes will be, and also the higher the elongation, and the better the properties. So the solidification rate can have a huge impact as well. We can see here, just to give a few examples, green sand or shell casting permanent mold, then die casting. So you can see that if you pour metal into a sand casting, well, it solidifies very slowly, and then it contracts and builds up a little air buffer that reduces the amount of heat that the mold can take out, and therefore it solidifies really very slowly. Permanent mold is much better, because the steel mold can take out more heat faster. And that's why we often see in sand castings actually little chill plates or chill blocks applied. The fastest way to solidify your casting is, of course, you push it very quickly into a thin-walled cavity in a die casting. And there we can see the solidification is much faster, and so we can get a different set of properties as well. Then, of course, it depends a lot on the casting design, the way we design our gatings and overflows. All this has a big impact on the mechanical properties that you can achieve. Then, the heat treatment, where there's a big trade-off, as I said before, between ductility and elongation. We'll get more into that in a different webinar. Now, if we look at the casting process in the USA, this is data from NADCA from January 2020, and you can see that die casting represents the larger share of the foundry technologies. So about 2/3 of all castings are made with the die casting process, while permanent mold and sand casting make up the rest. Within sand casting, we also find the lost foam and V process, and so on. And in the permanent mold, we find the low pressure permanent mold and the gravity and tilt pour process. If we look at the typical applications, we can quickly see that they are very different. For example, on the bottom you see a high pressure die cast engine block, which is relatively thick-walled and usually made in a 380 alloy. And then above it is a very different part. So that's a longitudinal member of a car body structure. So this would be a very thin-walled, I mean about 2 to 3 millimeter wall thickness. And it's also very long and a pretty big casting, which we will see later again in a different webinar. Now, on to the gravity or low pressure permanent mold casting. And there you can see an automotive suspension component. And the topmost picture is actually a huge sand casting in a high strength alloy for an amphibious vehicle. So you can see that castings can be made in very different shapes and with different applications with various alloys. Now let's start with the most common casting process in North America, and probably the world: high pressure die casting. It's really most suited for high volume production, and really high volume production. It's ideal for that because it's highly automated with an extremely low cycle time. sometimes in the range of 30, 40, or 50 seconds. Even for big engine blocks, you would talk about 90 seconds. And you can also have several cavities in one die, so you can make a lot of parts very quickly. The dies are very expensive, and so you would not make high-pressure die castings for a production volume of just 10, 20, or 100. Usually, high-pressure die casting is used when you have thousands, if not tens, or rather hundreds of thousands of parts to be made. Another beauty of high-pressure die casting is that it's very dimensionally accurate, so you get very tight tolerances, which can often help you save on machining later on. You can also make thin walls, so you can get down to 2 mm wall thickness. That's something you could not make in the other processes, at least not easily. And you can cast pretty complex shapes. When I say complex though, it still has to be possible to just open and close the die and maybe work with a couple of cores that you can pull out. But it's very difficult to have lost cores, like in gravity or low pressure processes. You will also get excellent surface finishes, even with conventional high pressure die casting, but especially if you apply a vacuum and use the right alloys, you will get a really excellent surface finish. The best of basically all casting processes. And you can cast from very, very small parts to very large parts, such as engine blocks or transition cases, and the body structure of castings, such as shown before. What's unique to this process is we have the so-called skin effect. So because you inject the die within milliseconds, it freezes on the outside within milliseconds, and has this very, very fine grain structure. So that has the advantage that you get a very sound skin, which helps you get excellent fatigue properties. So we can see this here in the picture, that the skin is super sound and we have a reasonably sound body. But the thicker you get, the more porosity you will find, and even more if you do not apply a vacuum. And that is a little bit the problem of high pressure die casting, with a very turbulent filling. So you will often get inclusions because you have metal fronts coming together, which also causes gas porosity and shrinkage porosity. Therefore, it's usually unsuitable for any structural parts, unless you do a few tricks to the die casting machine, which we will get to in a couple of slides. Within the high pressure die casting process, we distinguish between two major processes. One is the hot chamber die casting process, and this is only for low melting point metals right now. There, you actually put a plunger directly on top of the hot metal in the holding furnace. You push this down, and the metal is pushed through a gooseneck and a nozzle directly into the cavity. Now, a lot of people are playing around with this and trying to apply this to aluminum as well, but so far there isn't much success yet. So far, this is a very typical process for zinc or magnesium die casting. In aluminum, we typically work with cold chamber high pressure die casting. So it's actually not cold or room temperature cold. It's usually heated and at a pretty high temperature, but it's not immersed in the metal. So we would fill the metal into this cold chamber, and once the shot sleeve is filled, the piston then moves forward and presses the metal into the cavity. We also distinguish between two major machine types. The most common one is the horizontal cold chamber machines for horizontal high pressure die casting. And then we have the vertical die casting machines, in which case the piston is actually coming from the bottom and is pushing the metal upwards and into the cavity. This is mostly used for squeeze casting, but can also be used for the conventional high pressure die casting. So really here we are just distinguishing between the direction of injection or piston movement. Now, in high pressure die casting, as I said before, the molten metal is transferred into the shot sleeve or cold chamber either with a dosing pump from a dosing furnace or with a simple ladle. It's poured in there and then the injection starts. And we start with a slow motion. As mentioned before, it's called the slow shot. And we can see this here, until the metal is pretty much at the gates, and then the velocity is increased by a lot, and the rest takes place within milliseconds. At the end of the filling process, you usually want to slow down and then kick in the really high pressure to compensate the shrinkage, and that's called the intensification phase. So the process is divided into filling the metal in, slowly moving the plunger forward with a slow shot, then the high speed part, which we call the fast shot, and then the intensification phase. After that, it really just takes seconds for the metal to solidify completely, and then the die opens and the metal is extracted. The die is then sprayed with a lubricant and closed, and then the process starts again from the beginning. Now onto the problems with this conventional high-pressure die casting. And I say conventional because in this case it does not use a controlled filling like in squeeze casting, no vacuum is applied, and no reocasting is done. You do basically what you see on the right side of the top picture. You inject the metal at a high speed, and you can see there very obviously it's a very turbulent fill. With that turbulent flow, you have a very high risk of trapping air and getting inclusions and porosity in the part, and all sorts of problems that may not be immediately visible. So the casting might be fine, and that's why it is used for a lot of applications, because if you don't heat it to high temperatures, you won't see anything. And you still have the skin effect, so you'll have good fatigue properties. But it might not be suitable for impact, for example, and if you heat it up too much, you will see blistering because the gas porosity then expands, and the hotter the metal gets, the softer it is. It also cannot be welded, and certainly not brazed, and a lot of problems that you get when you have porosity appear. You also get shrinkage porosity, despite the high pressure to intensify it. And we typically therefore also have various types of inclusions, intermetallics, etc., because the high-speed injection of high-temperature aluminum. Aluminum has a high affinity to iron, and therefore the steel mold, so it would actually just stick to it. If you cast an A356 primary alloy like this, that is usually suitable for any other process in high-pressure die casting, it would just stick to the die, or it would solder to the die. To counter this, we usually have a high iron alloy, like A380, which is the most common die casting alloy. High iron also means it forms a lot of intermetallics and iron needles, which is how we see them in micrographs. These can block the flow, and they will be stress risers later on. So there are a lot of problems there, but for most applications we don't really care. Standard die castings, as we see here, have a density index that is relatively low, so you can easily see 2.5% porosity in there. If you apply some vacuum, you get that down to 1 or even 0.5% of porosity. But if you want a structural die casting that is completely heat treatable and weldable, then you have to apply a high vacuum and do a couple of tricks that we are going to get into. In order to avoid these problems of the conventional die casting, there are different types of what we call high-integrity die casting processes. And NADCA has a few books and standards for them that you can find at diecasting.org and download them from there. The most common process within the high-integrity die casting series is really the high vacuum die casting, also referred to as structural die casting. For this we need special alloys that actually have low iron, but the iron is compensated with manganese and in some cases with some strontium to beat the soldering. And then we also have squeeze casting, where we distinguish between direct and indirect, which we will get to in a minute. And there we can also use conventional foundry alloys, because as I mentioned, squeeze casting squeezes the metal in slowly, and it does not inject it at such a high speed as in high pressure die casting. And then we have the semisolid casting. There as well, you can use conventional alloys, but the beauty of semisolid casting is actually that we can cast different types of alloys as well that are much more difficult to cast. Semisolid is really just the way it sounds. You have a certain solid fraction that can be relatively low, just 20 or 30%, but also even 50%. So 50% can already be solid, and then the rest liquid, of course. This is nicely mixed and then squeezed into the die. The question is now, how do you get to this semi-solid status? It's almost like a soft butter that you're injecting into the die. Well, Thixo casting comes actually from a solid billet that has the size of your shot sleeve, and you heat it up in a very controlled way that it doesn't melt, but just gets to the semi-solid status. And there again you need special alloys for that have special microstructure. Or you would do what we call reocasting, where you can use conventional alloys, but also some special and new alloys. All these processes really allow us production of high integrity castings with very good properties that can be heat treated, are crash worthy, can be riveted, and you can do a lot of things with them. in a way very similar to low pressure or counter pressure castings, and they also offer, in addition, the advantages of high pressure die casting. Now, onto vacuum die casting, where we have to distinguish between different types. So there are two main types, the vacuum assisted and the high vacuum process. So if it's naturally vented, we have in our cavity 100 millibar, and there we just have some kind of opening in the die with a little chill block, and the air is supposed to just escape naturally. If you do vacuum assisted, you actually pull vacuum through the same type of chill block or through some kind of vacuum valve. They can be hydraulic, electrical, mechanical. There are many different types, but you pull the cavity pressure down before you inject the metal into the die and while you're injecting. Typically, with vacuum assisted, we talk about 200 to 400 millibar, while in high vacuum, which is really made for structural die castings that go into crash relevant body structures that might be welded or riveted, we talk about below 50 millibar, which is a really good vacuum. And as you can imagine, the more vacuum you're applying, the less porosity you will get. But you'll also see a big improvement in surface finish, and you can cast a lot more complex designs, and your minimal wall thickness is also reduced because you're not pushing against the air that enacts a counterpressure as you're pushing the metal in at such a high speed. The parts quality is also then very stable, and you get a lot less variation. If you're interested in these different vacuum technologies, you can contact Martin Hartlieb and he will gladly send you more information. In general, you get better mechanical properties and a better quality of the castings. So if someone tells you that vacuum just costs you more money, well then you are probably doing something wrong. Because if you apply vacuum where it makes sense and in the right way, it should actually help you a lot and should really reduce your scrap rate and make better castings. So in the end, it should actually save you money. A reduced wall thickness can also take more weight out of the castings, which is why a lot of body structure parts are made in this process. And it also allows higher part complexity, which is another reason why it is used for body structure parts. If you look at the high vacuum die casting process, the vacuum is very important. And you can see here in this picture that very often vacuum will be pulled from the shot sleeve, because this is where most of the volume of the air is, and then somewhere from the die, usually at the top at the last point of filling. And you can have that with one tank or with two, which is where you would talk about single-staged or two-stage. Martin also has various articles and webinars about this for NADCA. If you're interested, he can send you more information about that. In any case, vacuum alone is not everything. It's the same thing with the alloy. You can get the greatest alloy if you screw up the melting practices or handling practices. You can screw up everything. Here again, you can have the greatest metal and the perfect vacuum, and you can still not get good properties. So on top of vacuum, you need special alloys. The right alloys that have a higher purity than the typical A380, you need tighter tolerances, which doesn't mean that they have to be just primary, and that you can't recycle internally and things like that. These are all myths, and are talked about more in other webinars in this series. But what is very important is proper melt treatment and transfer practices. And there again, this is one of the key things, just like in any other high integrity foundry process. Very important in this case is also simulations, and special gatings, and overflow designs and vacuum gatings. Simulation is not an option for high vacuum die casting. It's really important, because you're talking about dies that cost you many hundreds of thousands of dollars, and you don't want to just try it out and see if it works. You also need very advanced die concepts, and very often you will see even inserts that are 3D printed with contour cooling and very sophisticated things. You also need a special cold chamber and shot system design. There are also special plunger types for high vacuum that can compensate for any wear that you would get over time. Special lubrication and lubrication types so that you have minimal application of lubricants is also a must. This is really just used for the production of structural castings, so shock towers, battery trays, those longitudinal members, and things that require heat treatment that are welded and riveted and such. Here is just an example from one of Martin's NADCA webinars. So you see the different parts that are typically high pressure die cast with high vacuum structural die casting for car body structures. So you see the shock towers on the top left, and at the bottom you see a high voltage housing There are cross members, there are door structures, there are all kinds of nodes, and they can be very long and very big. And of course, this is not just in a car body. This can also be in a snowmobile and a motorbike and in all sorts of applications. So now let's talk about squeeze casting. And we won't be getting into direct squeeze casting because that's called liquid forging, which is actually a better name for it because it's ultimately like a forging press, but instead of putting a heated billet that you would then forge into a final shape, you actually pour liquid metal in the bottom part of the mold and then squeeze down from the top with the other half of the die. And with that, you create your final shape of the part. It's a pretty rare process, and there's one place in North America that does it that I'm aware of. Of course, it is a high integrity process and makes very good parts. The most common one, nevertheless, is called the indirect squeeze casting process, which you can see here, for example. It has a very slow quiescent filling, meaning we don't get the die soldering issue that we have in typical high pressure die casting, and we don't have turbulent filling. We do still have the high pressure intensification stage, like in high pressure die casting, just with even more pressure. We get a very fine microstructure due to the rapid solidification, and we also get high tolerances. It is also suitable for thicker walls, so you don't get this typical porous structure inside, and you can also cast conventional alloys like A356, which can be a cost advantage as well. So this kind of casting competes with low pressure die casting. The problem is that this means high capital investment, so you're talking about millions of dollars in one machine, and the dies are just as expensive as with high pressure die casting. But now they also have a very short die life, making die replacement costs a really big item in your cost calculation. Typically, you also see graphite die lubes, which can be pretty messy. You can also have quite a few maintenance issues and a high mechanical complexity of the process, and therefore pretty high operating costs. Now, in squeeze casting, we can see all kinds of applications, but very typically you see like axle carriers, valve housings, here steering column housing, and suspension knuckles. We have also seen a lot of different types of wheels being made in squeeze casting, although I'm not aware of anyone doing this anymore in North America because it's very hard to compete with the low pressure process when it comes to wheels, and transfer cases are also typically made with squeeze casting. So now on to semi-solid casting. It is very similar to high pressure die casting. You're using the same die casting machine. You can even switch from one process to the other. This picture here is a typical picture you can see in any semi-solid forming presentation, that with a knife, you can just cut through the metal as if you're cutting through warm butter. So that would be the semi-solid slurry. As you can imagine, you get a very nice laminar filling of the die, not like in high pressure die casting, where the filling is very turbulent. The slurry has a very high viscosity and can therefore fill very thin sections as well. This makes it suitable for smaller and bigger castings with extremely thin and thick sections. The slower injection speed also avoids the die soldering issue of high pressure die casting. Like in squeeze casting, you can use conventional A356 but also a wide variety of special alloys, and you will get a very special microstructure. On the left, you can see a typical high-pressure die casting microstructure, which is dendritic, while the structure on the right, the semi-solid cast structure, is globular. The lower melt temperature increases die life, as you have reduced thermoshock and helps reduce cycle time. In semi-solid casting, we differentiate between Thixo casting and Rio casting. In Thixo casting, you heat up a billet into a semi-solid slurry and then squeeze it into the die. Typically, you won't have a melting furnace if you do Thixo casting, which means internal scrap recycling can be difficult and costly. That's where the idea of Rio casting comes in, because there you have a normal die casting setup. So you have a melting furnace, a holding furnace, and then a slurry maker, which means you can recycle everything internally. So you melt it with new ingots, and you go from liquid to semi-solid, and then you cast it. Often vacuum in this case doesn't really help, since you inject the metal in a slow and controlled way, and mostly into thicker walls. But now, there's a new process from Comtech in Sweden, which combines Rio casting and high vacuum. This kind of hybrid allows you to cast ultra-thin wall parts that only have 0.4 millimeter wall thickness, but also thick sections. There are more and more combinations and variants of riocasting. If we look at the Thixo casting process very quickly, the ingot is received. It is then electromagnetically stirred and cast into a billet with a certain microstructure. This billet is then cut into slugs. The slug is then heated in a very controlled way so that it doesn't start melting on the outside while it's solid on the inside. So it has to be in a very homogeneous way. Now, while it's still a semi-solid slurry, you put it in the shot sleeve, which is open at the top, and then you slowly push the slurry into the die. The problem is really the very high material cost for the billet and the inability to recycle the material internally. To avoid these problems, you can do riocasting, where you buy standard ingot and melt it down, and you melt it together with any of your internal scrap and gate and overflows, and then you have a certain process to convert this into the semi-solid slurry. You also still get all the advantages of Thixo casting on top of these advantages. The problem is it's very challenging to get a high quality slurry. Many of these processes came out, never had commercial success, and disappeared because getting the slurry homogeneous in a consistent way and not mixing in the oxide surface in the liquid metal is quite a challenge. Riocasting, as mentioned before, can also be combined with vacuum to make very thin walls. Looking at applications, we see on top, those are different applications for heat exchangers and filter boxes. You can see very thin rips there. In the middle, we have a 5G housing. Those are actually two castings, a top and a bottom welded together. On the right, we see suspension arms, and then on the bottom, we see a compressor and wheels and all sorts of things like that. So it can be anything that's usually high pressure die cast or squeeze cast that's high quality. New applications here, for example, are heat exchangers because we can cast new alloys or different alloys that have much higher heat coefficients. So now we get to gravity permanent mold casting, the second most common casting process in North America. And there we have a permanent mold made of steel typically, and then we pour the metal in, and that has to open and close, but it can also have lost sand cores, which is where we would talk about semi-permanent mold casting. The advantages are that you have several risers and feed paths into the cavity. We can also have multiple die carousels, which are very common for high volume parts. We also have tighter tolerances, better surface and mechanical properties than in sand casting, and the dies are by far not as expensive as in high pressure die casting, and it's still possible to automate the process pretty well. The disadvantages are the gravity fill, so fluid flow is critical. You really have to have a very good know-how about gating and risering. You can also easily have filling defects, oxides, shuts, and flow lines. And finally, dies are more expensive than sand casting, but still a lot cheaper than high pressure die casting. On to tilt pour permanent mold casting. You can see here a typical tilt pour mold. So it's similar to just an open and closed permanent mold, but in this case, we just need to be able to tilt it and smoothly fill the metal into the casting. We do this to get less pouring turbulence and a more consistent filling speed. You also have a less reliance on the operator skill that pours it in manually, and it also facilitates full automation. So in many foundries you will see these carousels, and they counter the downside of having the slow solidification, and therefore having a much longer cycle time. So here we're not talking about 30 seconds, but about minutes. But that does not really matter, because you're filling your mold somewhere, and then on the way around it solidifies, and then at the end you can take the piece out. This can significantly reduce your labor cost. The gating systems can be minimized, so therefore you don't have to throw away so much metal, and you get a much better yield. When it comes to gravity permanent mold applications, they're very diversified. Any parts requiring good mechanical properties, because you still have a relatively fast cooling compared to sand casting because of the cooling channels, you still get a very good surface finish, reasonable dimensional accuracy. It's ideal for medium volumes and for thicker parts than die casting. The dies are more expensive than sand casting, but are still at a reasonable cost. And examples are automotive parts, such as steering, suspension, knuckles, different engine components, and parts of building and construction, household appliances, and kitchen pots. Now, if you have to have voids inside a casting that you just can't make otherwise, where you can't put a core in there that you can pull out once it's solidified, then you can put in a sand core. This is later on removed. In this case, we are talking about a semi-permanent mold casting. Innovations in this process are, for example, inorganic binders based on sodium silicate with low emissions. Applications can be very diverse, basically any permanent mold casting that requires hollow sections. So now, after gravity and tilt pour, we are going to get into low pressure permanent mold. And of course, the advantage is that you have a high recovery to part ratio. It's simple, and you can cast thinner walls than with gravity. Therefore, if you look at typical applications, it's a lot of wheels. Pretty much all the wheels in America are made with this process. Then the disadvantages are that you have a single feed path, normally that's coming from the bottom through the upstock into the die. And you still have relatively slow solidification near the hub, and it's a much slower cycle time than high pressure die casting or squeeze casting. You usually have 1 or 2 dies per holder, and the scrap rates can run relatively high. As I said, most wheels are made in this process, and actually most suspension and structural castings that are reasonably thin-walled are made in this process as well. Now, there are different variations of the low-pressure process, such as the counter-pressure casting process. In this case, the furnace is also pressurized at the same rate as the mold cavity itself. After equalization, the furnace pressure rises, and the cavity is filled in a very, very controlled way. It remains pressurized until the cavity is completely solidified. This can also give you very high integrity parts. It's mainly used for automotive safety, critical castings, similarly to low pressure permanent mold. Now, you might have heard of the VRC or PRC process. So VRC stands for Vacuum Riserless Casting, and that uses a vacuum instead of low pressure to fill the cavity by pulling the metal into the cavity. And then PRC, which stands for Pressure Riserless Casting, which is where we pressurize the filling and solidification of the casting. Now you can have multiple fill tubes. They can fill one large or several castings at the same time. You can also highly automate the production rate and really make a lot of high integrity castings, like automotive suspension parts, for example. So now let's talk about a very odd process, centrifugal casting. So as you can imagine, centrifugal means rotating molds that are filled with aluminum. They're used typically, of course, for cylindrical or round and tubular shapes. Precisely pipes are made in this process. We have true centrifugal casting, and that eliminates the need for a core inside when making a hollow shape. So we see that in the picture on top. You also have vertical and horizontal drums, and then we have semi-centrifugal casting for solid parts that are symmetrical. We see this in the picture on the bottom. So you have a cope and drag and a flask around, and you can see the casting in brown. So the pouring basin is on top, and because of the spinning, you are distributing the metal nicely to the outside. When it comes to centrifugal casting, we distinguish between the axis of the mold and how the metal comes in. So here we see it is poured in and the molds are on the side. So the centrifugal force pushes the metal to the outside and into the mold during the rotation. So we have typically iron or steel molds, but also baked sand, plaster, and graphite molds. This usually gives a denser than gravity poured casting, and can offer the advantage of greater detail, a little bit like the low pressure casting. Application examples are typically tubes and pipes, but you can also find wheels, wheel hubs, motor, rotors, paper making, printing rolls, and things like that. You can also make fairly large castings in this process. Last but not least, of course, we still need to talk about sand casting. There also we see a lot of innovation, especially we now can have 3D printed molds that can be very big, which is also very interesting for making prototypes very quickly. We also know that sand molds are low investment, and that's really the big advantage here. You can have patterns made from wood, plastic, or metal if we want to reuse it many times, And the process is very flexible, also with respect to metal and alloys, so no other process would allow you to cast that many alloys. There are, however, many processes, and some are ideal for small production runs or prototypes, and some are really ideal for larger volume production. It's an ideal process for very complex castings. They can also be very big, as we saw in the beginning. This amphibious vehicle casting is very big in a high-strength alloy. You can see in the bottom picture, there are actually several operators filling metal at the same time at different locations. We also see precision sand casting for aerospace or entire door frames being cast. But of course, we will always have a very long solidification time, so a very slow solidification. And usually we need thicker walls. You can fill thinner walls in sand casting if you do low pressure sand casting, but that is a rather rare process. And you will always have this pretty rough surface finish because it is as rough as your sand mold surface. You will also get less dimensional accuracy and have larger tolerances. That's of course something that helps you with hot short alloys, because when you get hot tearing issues in a permanent mold because the casting is restricted but wants to shrink, well, here it is a lot easier for shrinking metal to push the sand a little around, which leads to the downside of less dimensional accuracy. In sand casting, you distinguish between different sands. So the most common one is the silica sand. You can also have olivine and zircon sands. You can see here their composition and grain size. We also distinguish between different binders, so they can be clay, organic, or inorganic chemicals, which is very typical, along with a catalyst. Then, for the classification of the process, the most common one is green casting. Green actually means wet sand, so the sand is not cured, and we pour the metal in there and use bentonite clay as a binder and water as a wetting agent. We also talk about chemically bonded sand, no break. We also hear cold box sometimes, which have organic or inorganic binders. There's also dry sand, so airiest, which has binders other than clay. Then we have waterless, so basically it's oil clay bonded sand. Then there's also baked or heat cured core sand. And lastly, we have shell, which is phenolic resin bonded sand. Continuing with sand casting, first we have pattern making, so we need a replica of the part, and that needs to be expanded a little bit to compensate for shrinkage. We also need to add some machining allowance if we have machining in some sections of the casting later on. These are usually made, as I said before, from wood if you're just making a quick one, or metal, aluminum, or cast iron. Core making, so any internal core is the same thing, any internal surface, voids in the casting, and then the mold making. The packing aggregate and sand is surrounding the pattern now. It's compacted, and when the pattern is withdrawn, the imprint is the mold cavity itself. So that's going to become the casting when it's filled with metal. We can also have chill blocks, and sand castings don't always just have one, but sometimes 10, 12, 15, so that you get directional solidification. So you solidify areas where you need better properties very quickly, or if you need to solidify bigger sections first because you couldn't feed them anymore. So all of this is possible. You also need very good melting and melt preparation practices, and then casting and pouring of the liquid metal. We see here an example. Usually you have some kind of gating system and a pouring cup. Often you would put a filter in there before the metal gets into the cavity. After that, it's the cleaning, removal of sand, scale, excess metal from casting, and then any subsequent process steps. We see here the process again explained in green sand casting. You often see the sand is made green, but really there's nothing green in the sand. It's just wet sand molds instead of dried sand molds, and the mold cures from the metal itself, and this is often a very highly automated sand casting process. So it's ideal for medium or high volume production of small or large castings. The whole thing is really flexible. And now we have precision sand castings, and they can be really high integrity castings, premium engineered castings, often for aerospace, for all sorts of applications that need high integrity but don't have the volume or need much bigger parts than you can make in permanent mold castings. With this process, porosity, inclusions, and other internal anomalies in the part are minimized, and the mechanical property capabilities of the material become largely a function of metallurgical structure. Optimal metal melting and melt treatment, gating risers, chills for directional solidification, etc. are all really key in order to achieve such great mechanical properties in such a casting, and the casting with the best mechanical properties of any sand casting process, with still pretty good dimensional precision and reasonable surface finish. It's used in critical structural applications in aerospace, automotive, and other industries, such as the nuclear industry, for example. Here you see the pretty rare process of low-pressure sand casting. It's used to make very thin-walled sand castings, for example, prototypes for die casting, and we've seen before it's a sand casting process with typical bottom filling but under low pressure, and it combines really the positives of both, but it still has a relatively slow cooling rate. Another special process is the Cosworth process, and here again it's sand casting but with bottom filling. The mold and core making is similar to conventional sand casting, but use a low thermal zircon sand for better dimensional accuracy, and silica sands are rather rare for this process. The zircon sands are pretty expensive, resin bonded and thermally reclaimed. The metal is in this case pumped with usually an electromagnetic or mechanical pump into the mold through the base using a relatively simplified gating system. You can see this in the picture. Very special is after the filling, the mold assembly is rolled over while it's still maintaining pressure from the pump. So the hottest metal is actually on top, and therefore we get a very nice feeding. And with this we can get very low porosity and very few inclusions that are normally common in other sand casting processes. This process also eliminates a number of minor problems of sand casting and reduces fettling time. Very typical examples are engine blocks and cylinder heads. Now, let's quickly look at shell molding or shell casting. And while the name kind of indicates what it is, it's basically a type of sand casting as well. But the heated pattern is placed in a box with sand and thermosetting resin. Then the box is turned around and the resin bonded shell is cured on the pattern. So we really just have a sand shell that is cured in an oven and then the pattern is removed. So we have two halves of shell molds that are assembled, supported by sand around it, or can even be also metal shot. In any case, the cavity is surrounded by a shell, and then the advantage of not having a completely cured sand mold is you don't have to reclaim this. You can use the sand endlessly. It's just the shell itself that we need to get rid of after. I'm sure you've heard of the V process or vacuum molding, but this is where a thin preheated plastic film is placed over a pattern, and then vacuum is applied to draw the sheet to the pattern contours, and a flask containing the mold is then filled with dry, unbonded silica sand, which is compacted by vibration. A second plastic sheet is placed on the top of the flask, and the mold is further compacted under vacuum. Then the pattern is reversed, and the vacuum is really maintained on the sheet as well as the molding box. The process is repeated for the other half of the mold. And then, with the vacuum maintained, because the vacuum really holds it in this position in the mold boxes, the pattern is removed and the two halves of the mold are joined and secured for pouring. After the metal has solidified, the vacuum is removed and the casting is released. So this way we do not need any binders and it's very easy to reuse the sand. Another special sand casting process is called lost foam casting. Lost foam because it's actually a styrofoam pattern that we are using. So you can see this here in the image, and it can be really very complex. And this is the positive shape of the casting. So these EPS patterns are coated with a ceramic layer, and then the sand is packed around it to hold it. Then the metal is poured, and we aren't getting rid of this EPS pattern. The styrofoam is really just burnt off. So the metal is poured in and it vaporizes the pattern and is cast in the part. So the strength of this process is it's extremely near net shape. So you don't need any draft or parting line because you're just coating and sand filling around, and you don't need to extract anything. You can therefore make pretty complex geometry without any cores, and you get a pretty good surface finish as well. The problems are the initial tooling. The pattern costs can be quite high. You also have a low pattern strength, so you can have a distortion in there. You also very often see casting defects like porosity and folds. You also have a beady surface finish, and you might see sand fill holes. Now let's have a quick look at investment casting, or lost wax casting. It's really ideal for very complex, thin-walled, intricate parts with high precision and a smooth surface. It's mainly for low volume, and you have a very slow solidification and pretty hot molds, so therefore you need a high purity alloy to make parts with good mechanical properties in this process. Vacuum, pressure, or centrifugal force can facilitate flow, and it's really mostly used for aerospace, military, very special applications, or for prototypes, for die casting, for example. So if we look at the process, we have injection or 3D printing of wax model. So you can imagine that can be done pretty easily, and it's not very expensive. And then we are mounting those. We call this a tree. And then the shelling process is where we put a shell around it. And then we have an invested tree, as you can see in the picture here. Then we de-wax the mold, so we melt the wax and it comes out. Unlike in the lost foam process, where we keep our pattern inside, in this case we get rid of the pattern before we pour the metal in. Then we preheat the mold and then we cast it. Then we have this casted tree, and we there cut off and finish it. And usually we would then do some non-destructive testing or heat treatment with it, and whatever else you would want to do. Another not so common process would be plaster casting. That again is very ideal for small volumes like prototypes, or for example the body of these crash test dummies. It can also be used for high volume parts. For example, here we can see a turbocharger impeller. Parts with high surface quality requirements, high complexity, and dimensional accuracy can be made with this process. You can also get very good tolerances, and you can actually cast pretty thin walls. This is a process that can really compete with die casting, except that you do not have the highest solidification rate, of course. So you have a slow solidification, and you therefore need high purity alloys if you want to get good elongation. And you'll end up having long cycle times, which makes it pretty expensive. But of course, your molds are not as expensive as in die casting. But you can use the same patterns and equipment like in green or other sand casting, or also stereolithographic rapid prototyping. The plaster contains additives, including ceramics, to enhance strength, permeability, castability, reduce cracking, baking time, etc. Usually you have 70 to 80% gypsum and 20 to 30% additives. The downside to this is it cannot be easily reclaimed. The process is performed by pouring liquid plaster over a pattern coated with parting compound. After usually about 15 minutes, you can remove the mold to be heated and dried in a special furnace for that. And that normally takes about 24 hours before the metal can be poured. Then the aluminum is poured, and after that the casting is removed and the plaster has to be disposed of. Now we get to the summary. We have seen a multitude of casting processes. We mainly distinguished between permanent mold, where we use the same mold over and over to make the castings, and lost mold. And within lost molds, we also distinguished between permanent patterns and lost patterns. So each of these processes has different advantages. It also depends on which alloy we want to cast, because some alloys are only castable in certain processes and not in others. And then, which kind of freezing rate do we want to get, or do we need to get? What is our casting size? What is our minimum wall thickness? What kind of surface finish do we require? Which kind of tolerances? What kind of initial investment can we accept? And which kind of casting costs do we want to have? And of course, there's always a trade-off. So usually, if you want to have low cost for the casting, you'll probably have a high investment in equipment and dies. So those advantages really determine the ideal application for each process. They can vary depending on the volume and special requirements. So sometimes you will make the prototypes in a small volume process, and then the high volume you make in a different process. And there are lots of innovations in alloys and processes enabling new applications and the entering of new markets. With this, we come to the end of this webinar. I would like to thank you for staying with us all the way through. If you have any questions or want to get more information, feel free to reach out to either Martin Hartlieb or Jay Armstrong. They will be happy to get back to you as quickly as possible. Thanks a lot, and goodbye.